Ladies and gentlemen, welcome to the next session of our tech session. For Q&A, kindly key in your questions at the Q&A chat box. Do visit our virtual exhibition and discover the latest water innovations and technologies. The exhibition will be live for 24 hours during this whole week. Do enjoy the next presentation.
We are coming to the final session of today at our hall 3. Now we have our speakers from UK, Mr. Paul Buck from Statiflo, International, United Kingdom. Good morning to you, Paul. In fact, we are in the afternoon now in Malaysia. Welcome to MIWC 2021 as our speaker. With this, may I hand over the floor to you. Thanks, Paul.
Okay, thank you. Good afternoon, and I suppose good morning if you're in the UK, but I'm assuming most people are in Malaysia. So good afternoon to you guys. Thank you very much for inviting me to present at the Malaysia International Water Convention. I'm very pleased to be here today to talk you through Statiflo's gas. Right, okay, so what we're going to look at today is Statiflo's gas dispersion system for ozonation applications. Now, to start off with, we're going to give you a bit of background information just about Statiflo, just so you know who we are and why we've got credibility to talk to you about ozonation applications using our gas dispersion system. So to start off with, a bit of a company profile. We are a worldwide supplier of static mixers. So that's all we do. We do different variations of different static mixers for different industries and different applications, but it's purely static mixers. Established in 1983, so we have been around for quite a few years now. Headquarters is in the UK, but we have offices in Germany, USA, and Canada, and a network of agents and distributors worldwide. We manufacture to ISO 9001 standards, so very high quality standards, and each of the mixers that we supply is custom built. We do have set designs of the internal mixing elements, but every mixer is built towards your specification based on the flow rate, the ozone gas flow, the pipe size, the required material of construction. We've got an extensive reference list of many different installations for many different applications around the world. We have many different installations currently in Malaysia and many in sort of Southeast Asia region, Europe and North America, South America. So many installations around the world. Wide range of applications. Obviously, we're looking today at water treatment applications, but we do static mixers for many different applications. And static mixers as well are suitable for continuous process industry. So any industry where you've got a continuous process, a static mixer is suitable to do your mixing in a pipe or open channel. Now, people will say, why use a static mixer? Part of the reason we're focusing on static mixers to start off with is because the gas dispersion system that we are promoting here, or that we're discussing, uses two types of static mixers. There's a main pre-dispersion mixer and then a contact mixer. So if we give you a bit of background information about static mixers to start off with, this will help with the overall explanation of the gas dispersion system. So why use a static mixer? There's two main reasons really. Overall, static mixers can save money. They can save money by using less chemicals, less energy. There's no maintenance requirement because there's no moving parts for the static mixer. There's no tank because everything is done in line. No electrical supply, and relatively a quite short payback period. We have had customers report static mixers to pay for themselves within 6 months of operation based on the chemical and the energy saving that they have achieved. Overall as well, achieve the process requirements. So by using a static mixer, you will better mix your chemical into your water or your gas into your water, and you will achieve the process requirement quicker. So overall, there's a benefit there. Right, what we're demonstrating here is pour mixing. So If you don't use any form of static mixer or gas dispersion system to mix your liquid or your gas into the water, what tends to happen is you get poor mixing and you get chemical overdosing. So what we're demonstrating here is we're injecting a red dye into the pipe. And you can see the dye is dropped to the bottom of the pipe here, and there is no mixing happening at the top of the pipe. So overall, this is an inefficient system requiring more chemical consumption than when using a static mixer. Now, just if we're focusing on this slide here, we've got two different images. Image one on the left-hand side is without a static mixer. And I think you can see without a static mixer, the red dye that we've used is clumped together in the middle of the pipe and is not properly mixed throughout the water. On the right-hand side, we have an image with a static mixer. And you can see that pipe is a nice even red colour through the full cross-sectional area, so that the static mixer there is completely dispersed the chemical throughout the water, reducing your chemical consumption and also achieving your process requirements. Now, this is where you can use static mixers on different applications on a water treatment site. You have initially some pH control, so potentially acid or alkali being dosed there. Then your coagulation phase, ferric sulfate, alum or PaCl, you can use a static mixer there to mix these chemicals into the water. The actual gas dispersion system that we're going to come on to shortly could be featured in two separate locations here. So we have aeration for ion removal, and also down here for ozonation. Obviously, we're going to go into more detail with regards to the gas dispersion system for ozonation there. Various other different mixes as well. We have mixes for polyelectrolyte into sludge, for sludge dewatering. We're going around here into sort of the disinfection stage. Your static mixers can be used there as well for mixing your disinfection chemicals in, whether that be an actual chemical or an ozone gas. And then a few different applications depending on what part of the region of the world you are. Fluoridation is not done everywhere, and plumb solvency, so orthophosphoric acid, is not also done everywhere. Right, how do static mixers work? So the clue is in the name with static mixers. There is no moving parts in the mixer itself. The way that the mixer works is by flow division and radial mixing. So you can see on this slide here, on the left-hand side, we have a helical twisted mixing element. And what this is doing, this is splitting the flow with the first mixing element. So you get 50% of the flow travels down this side, another 50% down the other side, and you get radial mixing happening as well at each element interface. The next mixing element is offset 90 degrees, and then flow division is happening again. So flow division and radial mixing. So as well as the flow division, you get radial vortices created on each of the element interface, which also assist the mixing. So it's flow division, radial mixing. Now I have actually got a video that I'm going to play here. So this is just a demonstration video of how static mixers work in their performance. So we've used a red dye again to simulate the dosed chemical. So if I press play on this video, hopefully this works okay with the slight time lag. You should be able to see that. Normally the chemical will be dosed via the yellow injection lances at the upstream end. But what we've done here is just randomly dosed the chemical at different locations just to show the performance of the mixer is still very good. You can see a slightly better angle as the camera pans up here. So that's your overall process. You can see the mixer is not moving itself. It's relying on the flow of the water through the mixer to divert that chemical and split the flow and create radial vortices. Right, what we're going to focus on now is some information just with regards to ozone gas, and then specifically we're going to move into the gas dispersion system. So I think we've got an idea of how static mixers work now. So as it says here, ozone has a very high oxidity potential, double that of chlorine. So it's very effective against a wide range of fungi, bacteria, and viruses. Ozone generators are also becoming more efficient. I think historically they were quite, the power consumption was very high, but they are becoming more efficient. So ozone is being looked at around the world for, you know, disinfection purposes, kind of as an alternative to chlorine. CapEx and OpEx costs are also lower than ever with regards to ozone systems as well. Right, the use of ozone is all around the world. Partly this is to do with, you know, regulation. Can be easy to use on sort of more complex systems, and there's a growing range of different applications where ozone gas is being used as well. If you can see on the slide here, this is some information that we've taken from the International Ozone Association, and there's a few different industries you can see. You've got municipal water treatment, industrial applications, food applications, and also medical applications as well. So the use of ozone gas is definitely increasing. However, it's important to have a good system to introduce your ozone gas into the water. Now, what we're going to focus here is some information on gas liquid mixing. Now, to start off with, if you were just going to use a standard static mixer, the static mixer provides a high shear rate, and the way that the gas liquid mixer works is the bubbles decrease in size as they pass through the mixer. So you've got your main water flow rate, your gas will be introduced, your ozone gas, and you can see the bubble size is decreasing slightly with each mixing element. So the terminal bubble size will be achieved at the mixer discharge. So what we're doing with a gas liquid mixing application is we're shearing the gas bubbles down to a small size, so you've got a higher surface area, and then you can achieve a greater mass transfer efficiency. With just using a standard single pass system, you do need quite to generate that bubble size. One of the main advantages of the gas dispersion system is it takes off a proportion of the side flow, which is re-injected back into the main pipe. But if we just skip through to the next slide, this is what we're actually featuring here. So this is our gas dispersion system. So what I'm going to do, I'm going to talk you through the actual components of the system here, and then as we move on, there's another video that will play which will give you an idea of actually how the system works in operation. So as I mentioned previously, it's a two-stage static mixer system. So you've got the main water flow rate, then roughly about 5% of the main flow is taken off via the side loop. So we have duty standby pumps positioned here. Obviously, if one of the pumps fails, you can quickly switch over to the standby line. So the purpose of this pump is purely to draw this water from the main flow rate. Then as we come back here, the gas will be introduced via a venturi. So the ozone gas is drawn in under low pressure. Then we have our first static mixer. If you remember, this is a two-stage static mixer system. The first static mixer shears down the gas bubbles to a small size. So you've got small, evenly sized gas bubbles, and then they are re-injected back into the main pipe where there is an additional contactor static mixer, which is then distributing the gas bubbles over the full cross-section of the area. So like I say, two-stage mixing system here. Now what I'm going to do is play this video because this will give you an overall idea of how the system works. I do hope that this video runs in real time. It may be slightly slow, but we'll see. I'll play the video anyway. Okay, so let's say main flow rate, then about 5% is taken off via the side loop, via the pump, if you remember from the previous slide. Gas is then introduced into the system via this gas venturi, so the ozone gas. You can see we've got quite large, inconsistently sized bubbles. Then we have the pre-dispersion static mixer, which is shearing the gas bubbles down to a small, uniform, even size. Then this gas liquid rich side stream is re-injected back into the main pipe, into the main contactor, where there is an additional larger static mixer, which is mixing that gas liquid rich side stream into the full volume of water. So let's say two-stage system. One of the main benefits is the gas bubble size can be maintained even with large variations in the main water flow rate. We're also achieving sort of very small micron bubble size, so the mass transfer efficiency for the gas dispersion system for an ozone application is guaranteed at 95%. So obviously a very high mass transfer efficiency. Now, the way that the pre-dispersion mixer works, I'm just going to play this. There's another video embedded in here as well. So this is how the static mixer shears the gas bubbles down to size. So I'm going to play the video here. It's an animation, but it's a true concept. So you can see larger gas bubbles coming in, and they are broken down and sheared down via the static mixer elements. So you get a consistent bubble size at the mix and discharge, leading to a higher mass transfer efficiency. I'll just play that one more time. You can see larger gas bubbles coming in, and they're sheared down to a small, evenly consistent size at the downstream end. Right, what we're going to look at now is some alternatives to the gas dispersion system. You may be aware of some of these alternatives here. So firstly, to start off with, it's just direct gas injection. Now, without any static mixer. So this is a very simple solution. There's no control over the bubble size, and there's no control over the bubble distribution as well. What tends to happen with this system is the gas is introduced, and then it goes straight to the top of the pipe, and it bounces along the top of the pipe. Now, obviously, that's a very inefficient system. You will have water at the bottom of the pipe not being treated, so you'll get a very sort of low mass transfer efficiency. Overall, quite a poor system. The second alternative to the gas dispersion system would be gas diffusers. These are fairly basic solutions with no moving parts. They do generate relatively large bubbles. There's no mixing because the bubbles just rise directly above the column where they are released. The bubbles also recoalesce as they are released from the diffuser. So as soon as they recoalesce, they travel to the surface quicker. So you get a relatively short contact time as well. We just go on to the next slide. You'll be able to see. This is what I'm talking with regards to some diffusers. They can have, with the bubbles being released here, coagulating together and then rising very quickly. So you've got areas of water here, here, and here, which are not being treated. So let's say the bubble size varies depending on the flow. This is different to the gas dispersion system where it's got constant fixed bubble size. Tends to require sort of quite high maintenance as well. The diffuser domes can become blocked with dirt and sediment, and they do need regular shutdowns and acid wash requirements to keep these clean and keep these completely sort of functional. Right, what we're going to look at here, this is a case study. So this is some gas diffusers versus the Statiflo gas dispersion system. This was a customer that contacted us in the Czech Republic in Europe. They had a ozone system where they were using a diffuser bed. Now, the initial mass transfer efficiency was 80%, but this dropped off to approximately 60% after 6 months of operation. So obviously they weren't happy with the drop in mass transfer because that meant they were required to generate more ozone gas. They had a more expensive system to operate. So they actually contacted installing a gas dispersion system. So what we did, we came along, we installed a gas dispersion system. So the bones of the system were put in this chamber here. So you can see that is your water takeoff. There is your pump, and you have your pre-dispersion mixers positioned here. And then there is the secondary contactor static mixer. What we also did was included stainless steel baffle plates here as well, just to increase the residence time sort of through this chamber. So the mass transfer efficiency increased to 98.5% using the Statiflo gas dispersion system. This resulted in an ozone electrical generation saving of €150,000 per annum. So the customer managed to save that amount of money just by increasing the mass transfer efficiency to 98.5% and by not having a previously inefficient system with the diffuser system. Right, this is an image here of actually an installation that's installed in Spain. So just to give you an idea, the pipework can be mounted in various different options. So there's a manway there just to check there's no blockages. This is not always required though, but you can see you've got your takeoff points there. There was 3 duty loops required on this system. So there's 3 pumps, pre-dispersion, static mixer, and then re-injected and back into the main flow right there. So GDS benefits to overcap. You get a high performance over a wide flow rate range. So irrespective of the main flow rate through the main pipe, if this flow drops to be very low, the system will still perform very well because it has an independent side loop that runs at a fixed flow rate. So even with a drop in the main flow, you'll get high performance over a wide flow rate range. Excellent transfer efficiency. We guarantee 95% based on good contact tank design as well. But the lowest recorded mass transfer efficiency has been 98.3%. So it's always been higher than that 95% guaranteed figure. Overall as well, quite a low pressure drop. There is a pressure drop overcoming the main contactor mixer. However, this is normally quite low. What we can do as well, we can tweak the design of the gas dispersion system to offer a lower head loss as well. So we could make the mixer a bit longer and drop the head loss pressure drop. That is a problem. Just some benefits continued. There's no deterioration of performance after prolonged use. You know, unlike diffusers, which do deteriorate in performance over time, for a gas dispersion system, there's no deterioration over time there. Everything is, is fine to be operated for a continuous period of time. There's only one moving part, and that's the pump. The system, apart from the pump, the system has no other moving parts on there. And like I say, that can be duty only, or we can have a duty standby pump on there. And they're always as well quite low energy consumption pumps in comparison to say like a jet mixing system, which will have pumps featured on there, but these are much higher power rated pumps. The gas dispersion system tends to feature quite a low energy consumption pump on there just to draw that water off. But all in all, it's very low energy consumption. Right, it's worthwhile mentioning as well that the Statiflo gas dispersion system can be used for AOP, so advanced oxidation process. As it says here, AOPs can reduce the concentration of contaminants from 100 ppm to less than 5 ppb. Now, it's very straightforward to convert a GDS to also perform the advanced oxidation process. All we need to do is to add a chemical dosing point and a mixer potentially upstream in order to add the hydrogen peroxide into the system as well. I think if we move on to the next slide here, there's a few different variations of AOP systems. So we can have the standard gas dispersion system with the hydrogen peroxide dosing point just featured on there, and it will be mixed throughout the water using the standard contactor mixer. Or we can have a completely separate standalone mixer where the hydrogen peroxide is added upstream and then mixed before the gas dispersion system. There might be some benefits there to have the hydrogen peroxide mixed before, rather than the hydrogen peroxide and the ozone trying to work at the same at the same time. And then the final sort of solution is to have a two-stage system, but into one, really. So we're still dosing the hydrogen peroxide, and then there's a couple of static mixer elements before the ozone gas is introduced into the system. So we can look at many different designs here. It all depends on sort of space available, whether or not you would like to mix the hydrogen peroxide in first, or whether you prefer to mix the hydrogen peroxide and the ozone gas together. So many different options that that we can look at for these systems as well. So I think when you're considering an ozone system, specifically looking at the gas dispersion system, do remember that we can offer this as an AOP system as well. So definitely. Right, okay, and that's it from me. So I'd say thank you very much for your attention. I do hope that was worthwhile. There are my contact details featured on the slide there. So if anybody does have any additional questions that you think of over the next few weeks, if you don't want to ask anything now, then feel free to get in touch as well.
Thank you, Paul. Well, one question from the floor, Paul. Two questions actually. From Gilbert, SCP, I presume this is from Sarawak Energy Berhad. The question is, does static mixer works well when operating well below the design flow? Sorry, the design flow rate or velocity?
Yeah, I suppose to answer that question, if you had just one fixed static mixer, then the static mixer will be subject to performing not as well under a lower velocity. Equally, under a higher velocity, you do risk damaging the static mixer. But if we focus or offer a system like our gas dispersion system, because this has a side loop where about 5% of the main water is taken off, where the ozone gas is re-injected there, that system, so specifically the gas dispersion system, can operate irrespective of very low mainline velocities and very high mainline velocities. So that system is unique in the sense that it doesn't conform to the sort of standard views of static mixers. So if you have a standard mixer with no side loop, then yes, you have minimum velocities, you have a problem. But with the gas dispersion system, it can handle very, very low mainline velocities.
Right. So there's another question. It said this. The question is, a side stream injection system required a set of multiple pumps, which will increase the plant operating cost compared to diffuser system. What is your opinion, Paul? This is
I suppose
some comment.
It is a fair comment, definitely. You're right. In comparison to a diffuser system, then because the Statiflo gas dispersion system does use a pump, generally quite a low power consumption pump, but there is a pump on the system, correct? Then yes, it will have a higher power consumption. But I think what we tend to say that with a gas dispersion system is the initial civil engineering cost is much lower, because for a diffuser system you need to build the diffuser bed and the tanks. With the gas dispersion system, it can be done inline in a pipe entering into the contact tank. So there is definitely an initial saving with regards to less civil engineering requirements. There's less contact tanks requirements using a gas dispersion system.
Right. I hope, Gilbert, is that the answer that you okay for you? If not, you can put up your question. There's another third question from Azro Haizal Hussein. Question is generally between fine bubble diffusers and injection system like Statiflo, GDS, which will create greater head loss.
Sorry, between which systems? So the Statiflo gas dispersion system, and what was the other alternative?
The comparatively, I mean, between, okay, the question I read again, generally between fine bubble diffusers,
Right, okay, yeah.
And your system, which will create, which were created greater head loss.
I think it would be similar. It's difficult to say exactly. The only thing that I can say is that you'll be quite surprised with regards to the Statiflo gas dispersion system, how low the head loss is. It's never a very high figure. You know, we're talking, if we have anything above sort of 100 millimeters of head loss, we consider this to be quite high, and we can change the design in order to reduce the head loss and keep it quite low in that sense. There's different things that we can do to the system.
Okay. Is the advantage of the system that you have is energy saving advantage. Even is the same head loss that we experience with two systems. Am I right to say that?
Yes, could be, yes, definitely. It could be, because it depends it depends what system we're being compared to. With regards to, say, a jet mixing system, the gas dispersion system will have much lower energy consumption. With regards to a diffuser system, it all depends on if there's any sort of pumping required to get the gas in, because there could be a higher energy consumption. It depends specifically on the diffuser system. But what I would say is the gas dispersion system, the power consumption is generally very low.
Right. The fourth question, probably this is the last question. Is it necessary to have the side stream that includes pre-disperser and pumps? Can we disperse zone gas? Oh, sorry. Can we disperse ozone gas using the main static mixer directly?
It depends, because you could potentially, but it would depend on a few variables. It depends on the main pipe size. If you have a very large main pipe size, the side loop system does have benefits. It also depends on as well if you have a fixed water flow rate or if the water flow rate varies, because if you've got a variation in the main flow, when you have a lower flow, you'll have bigger gas bubbles. So the benefits of the gas dispersion system is it keeps a constant gas bubble size. So if you were talking about a smaller main pipe, say down to 4-inch, you could potentially look at just direct gas injection with one main static mixer. But if you start to get to the size of a meter or roughly around a meter, maybe 800 nominal bore plus, this is where we would recommend a gas dispersion system, because you'll be injecting the gas, and even the main contactor mixer itself as a standalone mixer will struggle to shear the bubbles down to a small size. It'll tend to travel along the top of the pipe and not correctly move to the bottom of the pipe. So really for larger pipe work, where you have a variance in the water flow rate, the gas dispersion system gives you a controlled fixed side loop with a fixed bubble size. Alternatively, just doing a direct gas injection with a static mixer, the performance wouldn't be as good. Your bubble size would not be sufficiently reduced, and also the mass transfer efficiency wouldn't be as high.
All right. Thanks, Paul. I think our time is up. Should our audience participants in the whole tree have any more questions, you can always send email to direct to Paul or to our organizer. We'll definitely respond back to you. With this, I conclude this session and today's whole tree tech WC 2021 for day one, whole 3 is concluded today. Thanks a lot, Paul. Thanks, everybody. Thank you very much.
Thank you. Goodbye.
Bye-bye. Ali?